Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 10, Organic Chemistry 2. We are still in chapter 2, Aromatic Compounds. In the previous lectures, we covered introduction to aromatic compounds, nomenclature, structure, and stability of benzene, aromatic compounds other than benzene. Today, we will cover reactions at the benzylic position, reduction of the aromatic moiety. Reactions at the benzylic position. Oxidation. Even though chromic acid is a strong oxidizing agent, it doesn't oxidize benzene or alkane. So benzene with chromic acid, no reaction. Hexane, chromic acid, no reaction. However, alkyl benzene contains at least one hydrogen on the benzylic carbon. This is the benzylic carbon. Here we have in toluene 3 hydrogens. It oxidizes the toluene to benzoic acid, CH3 to COOH. Also cumene, here isopropyl group, this carbon, benzylic carbon, has 1 hydrogen. It oxidizes it to carboxylic acid, again benzoic acid. If the benzylic position lacks a proton, then oxidation doesn't occur. Like here, this is a benzylic carbon, no hydrogen, chromic acid, no reaction. When heated with aqueous potassium permanganate, alkyl benzene are oxidized to benzoic acids. See, so if you have toluene here, again benzylic with hydrogen, oxidizes, but because here potassium permanganate, so it forms the potassium salt first, so we have to add acid to get the free carboxylic acid. But if we do the reaction in base, again it will form a salt and we have to add acid. If we do the reaction potassium permanganate in acidic medium, then we don't have to add acid because there is acid already and we get the free acid at the end of the reaction. Draw the expected product when the following compound is treated with chromic acid. We have 3 substituents. We have this carbon benzylic with no hydrogen, so this one will not oxidize. This again benzylic with 1 hydrogen, then you expect this to be oxidized. This is the benzylic again with 2 hydrogens, then you expect the oxidation will occur on this carbon too. Well, we run the reaction and we get 2 carboxylic acids, and here no reaction. Free radical promination. Free radical promination occurs readily at the benzylic position with high regioselectivity. So if you have here benzylic with at least 1 H, we react that with N-bromosuccinimide, heat or light, we get the bromo compound. As we know, it's free radical bromination. So we have 3 steps: initiation, propagation, and termination. In initiation reaction, the traces of bromine present in N-bromosuccinimide will dissociate to free radical by light or heat, and that belong to Goldfinger's mechanism. Bloomfield, on the other hand, say, okay, the N-bromosuccinimide will dissociate to bromine and amide radical. Both initiation step creates bromine radical. In the propagation step, will react with alkyl halide, forming radical and HBr. And this radical delocalize over the aromatic ring to stabilize this radical, or according to the other mechanism, the amide will react with alkyl halide to form the same radical, same intermediate. This radical then react with Br2 to form the product, or this radical will react with N-bromosuccinimide to form the product, and the amide radical as a byproduct. Any two radicals combined together to give non-radical will terminate this reaction. So a real alkyl radical with bromine radical, termination. A real alkyl radical together combined to give again terminate. Amide radical with amide radical to give non-product, non-radical product. That's it to terminate the reaction. Benzylic radicals, cations, anions are stabilized by resonance with benzene ring. This effect allows for relatively easy radicals, as we have seen radical halogenation. Also affects SN1, SN2 reactions and benzylic anion formation. We have already covered the radical. What about the benzylic cation? See, if we start with the tosylate analog, and this is the benzyl carbon have tosyl group on, reacted with just sulfolysis here with ethanol, will go SN1 mechanism to form the ether. For the mechanism, the tosylate is very good leaving group to form the carbocation. This carbocation is stabilized by resonance with the ring. Okay, and this resonance structure, as we might know, will stabilize very well this carbocation intermediate. Then the sulfolysis, this will act as a nucleophile with its lone pair to form the oxonium intermediate. Deprotonation will lead to the final ether product. Benzyl halides and sulfonates undergo preferential and unusually rapid SN2 displacement in the presence of good nucleophile. As in allylic SN2 reaction, two factors contribute to this acceleration: inductive effect, resonance effect. So, for the inductive effect, the benzylic carbon is made relatively more electrophilic by the neighboring sp2 hybridized phenyl carbon as opposed to sp3 hybridized ones in alkane. The second is stabilization of SN2 transition state by the overlap with the benzene p orbit. Here sp2 carbon, you have here in the transition state, they are open to the benzene by system, so transition state is stabilized by such delocalization. So if we have bromomethylbenzene with cyanide ion as a nucleophile, the reaction goes SN2 pretty easy to form 2-phenyl acetonitrile. It's 100 times faster than SN2 of primary bromoalkanes. Again, bromomethylbenzene or benzyl bromide with sodium hydroxide will go SN2 to form phenylmethanol, or what we call benzyl alcohol. Resonance in the benzylic anions makes benzylic hydrogens relatively acidic. So if we have here carbon with one hydrogen at least, of course, abstracting this or dissociation of this to form anion, we will see that the anion here can delocalize over the benzene ring to form 4 resonance structures plus H+. This makes the anion stable via resonance. So toluene reacts with N-butyl lithium and tetrahydrofuran to form benzyl lithium. Very easy. Which molecule in each of the following pairs is more reactive with the indicated reagent and why? If we have here diphenylmethane and we have toluene, we react that with N-butyl lithium. Both of them will form anion. In the previous slide, we mentioned that phenyltoluene forms 4 resonance structures, while here in diphenylmethane we form 7 intermediate resonance structures. So more resonance structure, the more stable, the more faster the reaction will go. So we are expecting this hydrogen to be more acidic, and the formation of diphenylmethyllithium will be much more faster than phenylmethyllithium. Propose a plausible synthesis for each of the following transformation. Cumene to 2-phenylpropan-2-ol. So we have here benzylic hydrogen. We would like to change the hydrogen to OH. To do that, first step, treat cumene with N-bromosuccinimide to get the benzylic carbon brominated with Br. Then SN1 reaction to exchange Br with OH by treating this compound with water to furnish 2-phenylpropan-2-ol. How we can transfer ethyl benzene to styrene? Again, we have here benzylic carbon with 2 hydrogens. So we can react that with N-bromosuccinimide in presence of heat to form the bromo analog on the benzylic carbon. Treat that with potassium tertiary butoxide as good base and bulky one. The reaction will go E2 mechanism to form the styrene, elimination of HBr. gives styrene. Reduction of the aromatic moiety. Reduction of benzene needs 3 mole of hydrogen at 100 atmosphere nickel catalyst 150 degrees Celsius to give cyclohexane. The reaction is exothermic, gives out 49.7 kilocalorie per mole. On the other hand, styrene, this double bond can be reduced smoothly and selectively in presence of benzene ring, hydrogen at 2 atmosphere, platinum as a catalyst, and 25 degrees Celsius. Again, the reaction is exothermic, gives out 28 kilocalorie per mole. Compare that to propene, which has again one double bond. It gives out energy 29.5 kilocalorie per mole. These two values, 28 and 29.5, indicates that styrene is more stable and you get less energy out of heat of hydrogenation. Another reduction of benzene ring called Birch Reduction, named after Australian chemist who did this reaction. The Birch Reduction offers access to 1,4-cyclohexadiene molecules. So benzene, in presence of sodium, liquid ammonia, and alcohol, gives 1,4-cyclohexadiene. Mechanism: the sodium donates 1 electron to the ring. Here is homolytic fission. Homolytic. That leaves anion on this position and radical on that. So we have radical anion intermediate. Then this anion will react as a nucleophile, as a base, abstract the hydrogen from the alcohol, and then this radical will get another electron from sodium to form anion. Once again, proton transfer to form 1,4-cyclohexadiene. Reactions of arenes with positive inductive effect, positive mesomeric effect, substituents, lead to the products with the most highly substituted double bond. So if we have an azole, sodium, liquid ammonia, in alcohol like ethanol, you get 1-methoxy-cyclohexane 1,4-diene. Here you have the double bond, substituted double bond. You get that compound. This compound not formed. If you have oxoxylene, orthoxylene, with sodium liquid ammonia, you get 1,2-dimethyl cyclohexa 1,4-diene, not this compound. So you get the most substituted double bond. So in the first one you get this product, in the second one, orthoxylene, you get that product. Why that? How can you explain that? Let's take one more example. Reactions of arenes with negative inductive effect, negative mesomeric effect, lead to the formation of least substituted double bond, like in the benzoic acid, sodium ammonia alcohol, you get cyclohexa 2,4-diene 1 carboxylic acid. You get this one. This result can be rationalized on the basis of stability of the anion radical intermediate. When we have positive mesomeric effect, this anion will not be stable. Okay? Compared to if we reduce this carbon and form negative charge in here, first step. So this one favored and this one is unstable. If you have electron withdrawing with negative mesomeric effect in here, formation of the anion on this carbon will be stabilized by resonance, and this will be stable. Okay? See you next lecture.